I'm Jean-François Gagné. You can read my bio on the FOSDEM website. I want to take as much time as possible to talk about this subject and not me, so I'll start right away. So the title of the talk is The Consequences of Sync binlog Not Equal to 1. Actually, the full title of the talk should be The Consequence of Sync binlog Not Equal to 1 and of InnoDB flush log at TRX commit equal not equal to 2, because like one without the other doesn't really make sense. Like if you still sync InnoDB and you don't sync the bin logs, like you're still adding the cost of a sync. There might be edge case, but like that's what we're talking about. And I will use in the talk TRX commit for short because like this is just too long to write in slides. In the abstract of the talk, I say that it's faster, but we'll see by how much. Then we'll talk about what is replication and what are those two parameters. I'll talk about avoiding setting binlog to a value different than 1. And then the consequence, mitigating, and closing comments. So this talk is mostly about MySQL 5.6 and 5.7. Most of it also applies to 8.0. Some things about MariaDB, and I will explicitly mention it. And like, don't waste time taking pictures of the slide. They're online, and you can follow the slides right now on your phone if you're not able to see the lowest part of the slides. So faster by how much? So like we're in benchmark land here. So I used sysbench, single-threaded, insert benchmark without secondary index because I really want to test like the syncing part of MySQL on Google Cloud with SSD persistent disk MySQL 5.7.26. So sync binlog equal 1 and TRX commit equal 1. 200 transactions per second, single-threaded. This is not a lot. On the slave, it's a little more because here my client is remote from the master. So there's a round-trip time between the client and the database. On the slave, there's no such thing. If I reduce durability, so sync binlog equals 0, TRX commit equal 2, 3.7 thousand transactions on the master, 18 times faster. And 7,000 transactions per second on a slave, 30 times faster. So obviously, people having a replication lag problem, this is a very tempting configuration to do to solve a replication lag problem. But it has consequences. We'll see about this. The whole benchmark setup is discussed on one of my blogs. So this is what we're talking about. This is the speed difference we're talking about. Quick overview of replication. A transaction commit on the master. It goes in InnoDB and in the binary logs. Those binary logs are downloaded by the IO thread. Sorry, it's the lowest part of the slide. Are downloaded by the IO thread that connects to the master, download the binary logs, put them in the relay log. The SQL thread execute the relay log, put data in InnoDB, and eventually the slave produces binary log if log slave update is enabled. So sync binlog and TRX commit, they're here. Those are parameter controlling what happens on InnoDB on commit and what happens on the binary logs on commit, and they're also here. So sync binlog equal something, 0 to any number. Well, I guess it's limited by a size of an int. So sync binlog equal something. The binlogs are flushed to disk every something transaction. So if sync binlog equal 1, the binary log will be flushed to disk. So that means the data is actually on persistent disk, not in an operating system buffer after each transaction. If you set this to 0, the bin logs will be in the operating system, but you don't know if they're on disk. They will actually be flushed at every bin log rotation. There are some problems about this, but I won't go into the details. So this controls if our bin logs are persistent on disk or not. TRX commit can be equal to 1, 2, or 0. 1, the redo log, so the log of InnoDB, is flushed to disk after each transaction. 2, the redo log is written to the operating system. So it sits in the data sits in an operating system buffer, but is not flushed on disk at this point. It will be flushed on disk every second for InnoDB housekeeping. And 0, we're not really talking about this. It's like we avoid the system call at each transaction. The data is in a MySQL buffer, in an InnoDB buffer, and it will be sent to the operating system once in a while, every second. So that's what those two settings are controlling. So I mentioned flushed to disk. So this means that the data in an operating system buffer is actually persisted to disk. So this is not fast. So in old spinning Rust disk, a flush was taking 18 to 25 milliseconds. So that means we can do only 40 flush per second. So like 40 transactions per second. That's not a lot. Consumer grade SSD, so what you probably have on your laptop right now, it's very variable. A flush can take up to 10 milliseconds, and on some of the SSDs, it's 0.5 millisecond. Just do an I/O ping on your laptop. You'll know how much time it takes. Like enterprise SSDs, so all those are local disks, like 1/10 of a millisecond. If you have a RAID cache with a RAM, a battery backup RAM, it's 0.04 seconds. But we don't have only local disk. We have network disk, fiber channel, iSCSI, like any type of SAN. Like that's the network latency, 0.5 millisecond to 1 millisecond, depending on the efficiency of your network. And in cloud environments, disks are remote. So GCP or AWS, like between 0.5 millisecond to 1 millisecond to go to the storage. In AWS, you can have local SSDs, which are efficient, and that's fast. So like flushing to disk is not fast. And what does this mean? So what does this mean is that every transaction is durable, like sing binlog equal 1, trx commit equal 1. After each commit, transactions are on disk, so we don't lose anything. But if it's equal 0 or equal 2, if MySQLD crash, then the data is not lost because the operating system is still alive and it has the data in the buffer. But if the operating system crashes, we lose transaction. And also maybe InnoDB and the binary logs are not in sync. So here, if we do transaction A, B, C, D, and so on, maybe the binary logs are synced up to E, and InnoDB is synced up to K. And then we do other transactions and we crash. At recovery, the binary logs will contain up to E, and InnoDB will contain up to K. So we have a problem of consistency here. And there's also the other scenario where the bin logs are ahead of InnoDB. It's less, there's a less probability, but it can also happen. I'll skip this. So MySQL in 5.7 or 8.0 by default are, the defaults are not now safe. MariaDB defaults are not safe. It's not the best, like the choice here is theirs. I'm not sure I agree with this. So we would like to avoid setting send binlog to something different than 0. So the solutions here are either to get faster disks or to run things in parallel. And so a single sync will persist many transactions at the same time. So this is a binary log group commit on the master. Or if you use parallel replication, so if you run more than one transactions at the same time on slaves, maybe you'll be able to commit many things at the same time. So we'll explore this a little. So we remember the numbers. Very low transaction throughput with sing binlog equal 1. And as we use more and more thread, we're able to get a better transaction throughput. With sing binlog equals 0 and single threaded, we have a more decent transaction throughput. This is not with replication. This is with a client doing a round trip, so around 3,000. But this curve grows much faster than the other. So even if we're able to get a better transaction throughput with multi-threaded on the master, like we need 100, 200 threads to get a better transaction throughput. And since binlog equals 0, like we have better. So when you're looking for the best transaction throughput, like since binlog equals 0 is still better. This is with 4 vCPUs in Google Cloud, and this is with 16, so it scales a little. With replication, MariaDB has something called slave group commit, which is pretty exciting. It basically gets the transaction throughput of sync binlog equals 0 with many threads without the consequence of it. You can look it up. I have a link down there. And parallel replication on the benchmark I'm doing on the insert benchmark is like this is the worst benchmark for parallel replication because there's a lot of contention. Sync binlog equal 1 we scale, but with sync binlog equal 0 it's still better. So like we're still like tortured here. If we want the best transaction per second, sync binlog equal 0 is still our best choice. Those are all the graphs on the same page. So now about the consequence. So now we get in the real subject of the talk. This is a copy from the previous slide. So just remembering transaction A, B, C, D. Binlogs are synced up to E. InnoDB syncs up to K, and then we crash. Maybe it's a time for one question here before I move forward. Everything is clear so far? Okay. So let's see about the consequences of this. So if the master crash, so we're only interested in operating system crashes. Like if MySQLD crash, we don't lose anything. Everything is in a buffer. So if a master crash and we're using legacy replication, so file in position. So the slave is pointing in the binary log that will vanish. So after the crash, MySQL will create a new binary log, and if we keep writing, data will be append to the new binary logs. But the slaves are pointing to something that is now gone. So during the crash, the slaves are not able to connect to the master, but after the recovery, the slaves connect to the master, and they connect in something that doesn't exist, and then replication breaks. So that is obviously not cool, because if like now you lose all your slaves, you can still write to your master, which is kind of inconsistent. InnoDB and the binary logs are not in sync. You lost some data. The slaves has actually more data than the master because they didn't lose the last transaction. The master did. So you are not in sync, and with broken replication, this is really, really not cool. And if you have lagging slaves that are pointing in an old binary log, like they will keep going, but they will be like they will have corrupted data. So everything is out of sync, pretty bad. If you're running with GTID, so let's say at the moment of the crash, we have GTID up to 60 on the master, and the slave adds up to 58, and then we crash. Now the master goes back up, and because the GTID state is stored in the master, the slaves start back in the binary log. The slaves start back the master starts at GTID 50. And so it will write 50, 51, 52. But the slaves has already 1 to 58. But those are the old transactions. And now we have new transactions that have the same ID. So two things will happen here. Either the master will be able to write up to GTID 58 fast enough before the slaves reconnect, and then everything will work, but will have corruption. Or the slave will be faster. It will reconnect while GTID 58 doesn't exist on the master, and then replication will break because the slave has something that doesn't exist on the master, and that will break. So that's another scenario where things break here. And that's what I just explained. So that's in the case of an operating system crash. If the slave crash and we are using file and position replication, if we are using crash safe replication, basically the replication position is in InnoDB. So InnoDB will do crash recovery. that information will be consistent, and then the slave is able to restart, to reconnect to the master. It's still as binary log that we cannot trust because now they're out of sync. But there's no data corruption in InnoDB in this case. So if you're running with GTID with binary logs disabled on the slave, which is a feature of 5.7, the position, the GTID position is also stored in InnoDB, so there's no problem here. The data is safe. The binary logs on the slave obviously is out of sync with the data, but the slave will reconnect to the master, and the data of the slave will be consistent. But if you're running with binary logs enable, because the position of replication is stored, if you're running a slave with GTID and binary logs enable, 5.6 or 5.7, the GTID position of the slave is in the binary log. We crash, we lose binary logs, we're out of sync between InnoDB and the binary logs, and so we start replicating at the wrong place. So again, data corruption, either replication will break or we will have silent data corruption. So those are the consequences of running with this parameter. Something in MySQL 807, GTID position in InnoDB, unclear. There's hardcore reading about this if you want more details. And now we are at mitigating this. So if you're running with sync binlog not equal to 0, basically there's one thing that you need to remember, is that either on the master or on the slave, after an operating system crash, you cannot trust the bin logs. Like, obviously, you didn't sync them. You cannot trust the bin logs. So what can you do in a situation where you cannot trust your bin logs? So on a master, after restarting MySQL after an operating system crash, what I do is I make sure the master will restart in offline mode equal on. So no clients connect to it, no slaves, no clients, and then I decide as a DBA what to do. The best thing is to failover to a slave, but if I do not automate failover, if this is manual, I do not want clients to write to my master, and I do not want slaves to connect to it. And here I arrive as the DBA. I check if this is an operating system crash, in which case I need to failover, or maybe it's just a MySQL D crash, and then I set offline mode equal off, and then I continue, because at that moment I didn't lose anything. On slaves, on slaves, if MySQL restart after such a crash, if you have binary logs on the slave, like, you need to purge them. Like, you need to completely delete the binary logs, because now potentially you have a hole in there. If the slave will eventually be a candidate master, you cannot trust its binary logs. So wipe the binary logs on a slave. If you're running with GTID, a reset master will erase your GTID position. So you need to restore this. Intermediate master are both master and slave, so you have to do the two things. When you're running with GTID on a slave with sync binlog not equal to 1, so GTID replication is not crash safe. So normally, what you would have to do is you would have to restore a backup. And this is very annoying for a DBA to restore a backup. So there's a way to avoid this. It's because file and position in a table can be trusted at that moment. So if you're running crash safe replication, not with GTID, with file and position, there's some voodoo you can do here, either if you're running single-threaded or if you're running multi-threaded with slave preserve commit order. There's some voodoo you can do here to avoid restoring the backup. And so the idea here is when the slave restarts, make sure that replication doesn't start. You cannot start at this moment. The GTID position cannot be trusted, but the file and position can be trusted. So what you can do here is you note the GTID executed of that slave, and then you wipe the binary logs, reset master. Like the binary logs on that slave cannot be trusted. Then you restart replication with file in position, which is trusted. And then you need to restore the GTID position. And this you'll have to figure out by yourself. It's left as an exercise. If you're not able to figure this out by yourself, you shouldn't do this voodoo. So that's how I run my my slaves with sing binlog not equal to 1. So in conclusion, like we saw the consequence, we understood it, we understood how to avoid it, how to mitigate it. So I have a guess, an educated guess, that more and more people would run with sing binlog not equal to 1 because of the cloud. Syncing in the cloud is very slow. So you need to run with sing binlog not equal to 1 if you want decent TPS in the cloud. And so to be fully cloud ready, MySQL should make it easier for us DBAs to like run in the cloud. So basically I would like auto offline mode after an operating system crash and auto skip slave start after an operating system crash. And I have three rants on my favorite feature. So like GTID makes things very complicated. So there's a GTID state in the table, there's a GTID state in the binary logs, and now there's a GTID state not in the redo log, it's in InnoDB. So like there's cleanup to do here. And one last thing about GTID, like somebody left, but like this GTID state is just horrible. So like we need a way to clean that.
Just split it into multiple lines.
Sorry?
Just split into multiple lines.
Yes. So I have links in my slides. Classic thing, my employer is hiring. Please rate my talk. And I have time for questions?
Yes, you have 3 minutes.
3 minutes for question. Yes, Marco.
Yes, so as you benchmark the variation where the InnoDB redo would not be synced, and of course that needs some implementation which is on work for MariaDB 10.
Yes.
That the binlog would be guaranteed to always be ahead of
Yes.
the InnoDB log.
So the question is,
Less overhead, just sync the binlog.
yeah, so the question is, did I do tests about not syncing InnoDB? And the context of that question is that in some next versions of MySQL MariaDB, there will be features of keeping consistency without syncing InnoDB. So like removing a sync instead of having 2, like you'll double my results. Like 200 transactions per second will end up being 400, which is very far from 3,000. I haven't formally tested that, but I can do an educated guess here. So it's a nice improvement to remove a sync in InnoDB. Personally, I think it's not game changer. We're just changing by a constant. We're multiplying by 2. If I would have to choose between this feature, not syncing InnoDB and keeping things consistent, and making MySQL or MariaDB easier to run with sing binlog equals 0, I would choose this one. But like it's like different people work on different part of the server, so like it's still an improvement, but I don't think it's game changer. Other questions? Yes.
What about having sing log to 1, but the transaction log to 2?
It's basically, so the question is about having sing binlog equal to 1 and TRX commit equal to 2. Currently there will be inconsistencies like between the binlogs and InnoDB. It will remove one sync, like doing one sync on transaction commit instead of 2, which in the end is not game changer because like we're still waiting for this. So I haven't done tests and thought much about it. My intuition here, it's not, in the current context, it's not super useful. Any other questions? if I have time.
One last question. One last question.
Yes.
Would it make sense, or what's your view on, instead of trying to maybe handle clusters of mice, but like pets, handle more like cows, as it is commonly said, instead of trying to fix, either go to maximum persistence, everything
Yep.
to 1, or if you don't have the throughput, go to okay, it's crashed, let's fail over.
Yes. So the question here is, instead of taking each server and being very careful about the consistency of each server, thinking about like MySQL as like the full distributed system, and if the master crash fail over to the slave, this is the solution in the case where you have an operating system crash on a master if you're running with some binlog equals 0. You need to fail over to a slave. Because you potentially lost data and your slaves are corrupted. So yes, that's the solution. The DBA needs to think about not one server, but the whole distributed system, which is like replication is a distributed system. So we have to fail over. Yes. I'm not sure I have time for another question, but I will be out of the room. If you have questions for me, I'll be just out of the room and ready to answer your questions. Thank you very much.